Um, okay, so the topic was already given, and yes, my name is Sven Breitkopf. I'm the head of sales at Active Fiber Systems. But of course, this talk contains a lot of scientific content, which is obviously not my work. So I'm giving this presentation on behalf of all my colleagues. First of all, I would like to give a short outline. So of course, in the beginning, I would like to motivate why should you use fiber lasers anyways if you want to do any imaging or spectroscopy application. How is this done? So how do high power ultra-fast fiber lasers work, and how do you do some frequency conversion to cover the entire range? And then I will give a brief talk about, or a brief part of the talk will be about cars and SRS sources, which is a bit different to the second part of the talk. And I will conclude here and give a brief summary in the end. So first of all, the motivation for lasers and for high power lasers in general, typically you hear materials processing, secondary radiation imaging, spectroscopy, and very exotic applications such as particle acceleration. And while they are vastly different, they have some things in common. Typically, you always need some level of peak power or some pulse energy to enable the application. And if you want to do it fast, and if you want to have a high processing speed, high acquisition speed, and also good signal to noise ratio, at some point you will need a high repetition rate for these pulses. And that is typically where fiber lasers come into play. Usually for many applications, you have some certain requirements on the wavelength. So of course, there are some things you can do better in the XUV or better in terahertz, and particular in spectroscopy, you're usually fixed to some certain wavelength that you would like to have. But also, as I said, you need pulse energy, peak power. The spatial and temporal properties of the beam are important. And yeah, you might need some sort or some certain level of photon flux or average power to carry out your application. And you cannot cover the entire range with the laser directly. Thus, what you do is you start at a certain wavelength, and typically 1 micrometer is a good choice because there are high power lasers available there. And then you can use conversion mechanisms to go towards the XUV or towards the mid-IR. Or you could alternatively start at 2 micrometers, because this is also a wavelength range where you can build very high power systems directly, high power laser systems. And this enables the coverage of further parts of this electromagnetic spectrum. Yeah, so since you have limited conversion efficiencies, you need strong femtosecond lasers at 1 micrometer or 2 micrometer to have a good starting point, right? So this is what the first part of the talk will be about, and also where our company comes from. So the entire goal of our company, which was founded in 2009, is to have a rapid transition from ultrafast laser technology from the research into reliable, commercially available systems. And our main market as of yet is research, so research facilities all over the world. And you could say we are a technological leader for these high power ultrafast lasers. So we have many world records when it comes to average power. And here you can see we've been growing quite a lot over the last years. Also have a big building now in Jena. And I don't have time to do that now, but if you want, you can take a look at our laboratories. We have this virtual lab tour available on our website. Okay, first of all, maybe not all of you are familiar with fibers in general. So a fiber-based amplifier usually works in a way that you have a signal coupled into a fiber, and you have a low brightness pump light coupled also into the fiber, usually from the opposite direction, and then you convert the pump light into signal light and basically increase the brightness of the beam. So you will generate light with real good spatial and temporal properties in this amplifier. And because fibers usually have a very small core, of course, you are limited by the peak power that this fiber can handle. So there's some sort of limitation in the amplifier. And to go over these limitations, you have to use a chip pulse amplification scheme. I guess most of you are familiar with that. There was a Nobel Prize for it a couple of years ago. And so basically you stretch the pulse in time, you amplify it, and then you recompress it to a short pulse at the output. And the limitations I talked about in fiber amplifiers You can have damage issues at the surface, or you get nonlinear effects in the fiber, so you get an ugly pulse out of the amplifier in the end. You can have problems get away the heat from the fiber. So if we're talking about a couple hundred watts of average power, then these thermal issues can come into play. And also at a higher average power level, there are other thermal issues caused by the laser process in the amplifier, which are harder to circumvent. However, you have options to prevent these limitations from kicking in too soon. You can scale the area of the fiber, the mold area, or you can use parallelization. Okay, and first of all, this mold area scaling is something we've done over the last decades at the university and also at the company by developing fibers that have a very large core, and thus you have a reduced intensity in the core, and you can simply put more energy into the fiber and get more energy out of the fiber before you have any limitations setting in. And yes, the second one, the parallelization, is done by coherent combining. So what this means, instead of using one amplifier, you use many amplifiers, and simply before the last amplification step, you split the pulse into several replicas, you amplify it, and you recombine it. It's like in the processor CPU industry, basically. You use many CPUs instead of one. Yes, and this way you can ideally achieve laser parameters which are not limited by physics anymore, really, but only by how much money you have and how much footprint you can allow for. And this combining mechanism has already improved the output, the average output power of these ultra-fast laser systems quite drastically. So you can see there was sort of a saturation a decade ago, and nowadays we were able to improve this by more than a factor of 10 already. So this is really interesting technology for scientific applications in particular. Okay, this is how it looks in the lab. And some values we can achieve nowadays, so up to 20 millijoules of pulse energy, 2 kilowatts of average power with ultra short pulses, so 250 femtoseconds, excellent beam quality. And also this is available at different wavelength. So I was talking about 1 micron and 2 micron, but of course you can also have some conversion to other wavelength. But it reduces energy and average power. Also we have software and interfaces ready for these systems and developed for customers specifically or in general. And especially during the pandemic, it was very helpful that we have these extended remote service options. So lots of the things can be done remotely, even installations. So this was very helpful when exporting to the US or China over the last year. Okay, but let's get into imaging and applications. So what I just showed you basically is this. This is the product portfolio we have. So there are some more things I won't talk about today, but these high power systems are shown here, and we also offer post-compression techniques if you need even shorter pulses, and the conversion to the XUV range, which I will focus on now. So you can combine these things like modules basically, and we optimize the specifications according to what you need, what you want. The high harmonic generation, maybe many of you haven't heard of that before. It's basically a mechanism that allows you to convert visible or near infrared radiation into XUV radiation. So this happens in the gas jet typically, and so you simply send in a lot of power at the infrared, and then you get out some XUV light. And this XUV light, of course, has a very short wavelength, so it's ideally suited for imaging applications. And since the conversion efficiency is in the range of 10 to the minus 5 to the minus 7, you need to send in a lot of average power to get out a reasonable amount of flux and average power to work with. So that is why you need a very strong laser to begin with in order to have something left at the end. And don't be intimidated by this plot. It simply shows the photon energy, which is sort of a measurement for, or it's the wavelength. So higher photon energy means shorter wavelength in the XUV, and the average power that was achieved at these photon energies. And this is these are some record values that were obtained over the last 2 decades in different labs worldwide. And the blue lines and blue measurement dots are acquired using fiber lasers to drive these high harmonic generation. And you can see that fiber lasers really excel when it comes to high average power in this XUV regime. And this is what you need to get a good contrast in your imaging applications. You need high average power for the XUV radiation. So here you can see these fiber laser results, where most of them were obtained by our company or the Institute of Applied Physics, which is where we are a spin-off of. Okay. One application, I said imaging applications, but what sort of imaging application do you do using XUV light? A very popular application is coherent diffractive imaging. And the idea is basically, this is again how you generate the XUV light, and you focus it on a sample which you want to image. And instead of using XUV optics behind this sample, you simply look at the diffractive image. So you don't need any optics afterwards. You capture the diffractive image. So this looks like this. You have, for example, an object like this. You get the diffractive image of that. And then you can use an algorithm to calculate how the image originally looked. And since you are having very short wavelength that you're working with, in this case, maybe a dozen nanometers, a couple dozen nanometers, you get a very high resolution in the end. So here the resolution was 13 nanometers of this object. So this is highly interesting for a semiconductor industry, for example. Okay, let's get a bit more into some specific things that you can do using 2 micrometer lasers. So these results were done with 1 micrometer lasers, but if you change the wavelength of the driving system, you have you can access other ranges of this electromagnetic spectrum. And we've built a system. This was a couple months ago or a year ago, maybe. As you can see, it's a scientific system, so it's on an optical table. And this box basically contains the oscillator and this entire pulse amplification scheme, so a stretcher, some preamplifiers, main amplifiers. There's also a combining system. So you use many parallel channels. And this is the compressor, the CPA compressor. And at the output, the system could deliver 200 microjoules, 600 kilohertz, 110 watts of average power, which is quite a lot already, and sub 120 femtosecond pulses. And this system is being used for coherent diffractive imaging applications right now. And basically, we are working on a transition of such a scientific platform, as I showed before, this one, into a more compact, more industrial grade platform. And this is something we have almost finished at the moment. So in a couple of months, we should be able to show a real industrial grade Thulium system. Yeah, there are other things you can do with Thulium. You can also use it to generate radiation in the mid-IR regime. As I've showed in the beginning, you can go to short wavelength for the XUV. You can also go to longer wavelength, which can be interesting for molecule fingerprint region. So you have different resonances of molecules in that region and can distinguish them. And this is a result that was obtained a couple of years ago at the university, actually, with the same technology we are using now. And you can see they achieved a much higher brightness compared to typical synchrotrons. So nowadays, if you want to do imaging in this wavelength range, you might have to go to a synchrotron, and that works well, but you need to get beam time, and it's a lot of effort to get your experiment there. And using a Thulium laser and a mid-IR conversion can enable you to do these experiments in your own lab or in your own company. And also what I said before, these high harmonic generation again. But the advantage is if you start at 2 micrometer, you can go to really high photon energies. So up to a few hundred electron volts or even higher. And you can see here was a signal up to 350 electron volts obtained. This is only to show that the signal is real and not noise. This is an additional filter that blocks this light to make sure this part of the signal is real. And this allows you to do different imaging applications that you could not do at lower photon energies because simply you were not in the water window as of yet. Yeah, so this is a very exciting application as well for these 2 micrometer systems. Okay, some more words on imaging, but in this case, cars and SRS sources. So coherent anti-Stokes Raman scattering and stimulated Raman scattering. The idea here is you use basically 2 wavelengths, and the difference between them is what excites your probe, what you want to look at. And it allows you, for example, to distinguish between lipids and proteins, which is extremely helpful, for example, if you want to distinguish between healthy tissue and cancerous tissue, because the ratio of these changes. So this is very interesting for medical applications if you want to take a look, or if you want to observe the tissue of a patient and make sure you can tell if it's cancer or not. And yes, the advantage is you have a nonlinear response, so you get a much better signal-to-noise ratio due to this mechanism. And you could also investigate living cells. So these systems, they are running at a lower average power, so it doesn't destroy the cells. It can work quite well for living cells as well. Yeah. And this is how such a system looks, for example. So this they also have a fiber-coupled output, so they are easily integratable into microscopies or microscopes. And this just shows how the tuning works. It's a bit too specific right now, maybe. But in general, these systems are very compact, turnkey, air-cooled, and you can control them via software. And you can address a wide range of resonances. Typically, you only need the range below 3,000 inverse centimeters, but sometimes for different molecules, different different things, you need different ranges as well. And the tuning speed is very high in the range of seconds to tune over this wavelength range. So you can actually have a video time imaging. This is an exemplary image of such a device. So here you can see some human perivascular tissue, and you can distinguish the lipids, proteins, and collagen in this tissue by using different sorts of signals coming from the same laser system. And this is very helpful, of course, because if you just looked at this with a standard microscope, you couldn't really tell the difference that well. And also the advantage of this mechanism is you don't need any marker. So there's no chemical marker that you have to insert into the patient. Usually this can be a problem because they cause allergic reactions. It's difficult to have these markers approved for medical applications. And if you don't need markers at all, this has some huge advantages. Yes, we also have a couple of research projects going on with these sorts of systems. For example, in this project, we are trying to not only have the imaging done in a compact system and microscope, but also the removal of this tissue. So you can take a look at it. And for example, here you can see this part. Apparently, I cannot tell, I'm no expert, but the experts can tell that this must be removed. So this is bad, apparently. And you can directly use the same system, but of course a different laser that goes through the same fiber to remove this part of the tissue. And this is very promising for to reduce the time frame the doctor needs to treat the patient for such cases. But of course, this is in a very early stage at the moment, and we're currently working on it together with the clinic in Jena and a couple other partners to get this done within the next years. Okay, to conclude, I wanted to show you that the electromagnetic spectrum obviously is huge, but you can access a large part of it using a 1 micrometer or 2 micrometer high power lasers. And this is important because if you use them to convert the radiation to these different wavelengths, you maintain the great temporal and spatial equality, and you can get very high powers that you couldn't get otherwise as well. Also, we are typically focused on providing customized solutions for individual requests, but we have a few product lines that are basically off the shelf. And depending on the parameters a customer needs, we can typically offer a solution for that. We also, that is something that I haven't showed you yet, we also offer more complex scientific systems. That is actually a big part of the requests we're getting, where people want to do photoemission spectroscopy or angular resolved photoemission spectroscopy. So there's a big field of different photoemission spectroscopy applications nowadays, and this is really of high interest in the scientific world right now. Yeah, so in general, these 1 and 2 micrometer high power sources enable a vast range of applications, and I hope I could give you a brief introduction in what they are capable of. Thank you.